Okay, today we are going to derive the formula for the derivative of a to the x. So that would be any a to the x, where we're letting a to the x equal y. So any equation, including or even just standing alone, of a number base with a variable exponent. So a constant base with a variable exponent. So there's going to be two ways to do this. I've seen it both ways. I've found them both interesting and helpful, whichever one you like best. I mean, they both lead to the same solution, but the first one I'm going to do is when we rewrite a to the x as a base of e. And we're using a rule here that e to the ln of anything at all. So it doesn't matter. It could be pancakes. In this case, it's a. Is the argument, is a. And then we're going to raise it to x because we're not just dealing with a, we're dealing with a to the x. And then we can multiply these two right here. We can multiply those. So they just become one exponent. Okay, so the first thing that we're going to do is we're going to just take the derivative of both sides. So we're going to derive this using implicit differentiation. It's when you derive both sides of the equation separately. And we're going to also remember that we have made a to the x equal y. So we're actually going to derive y with respect to x, which is going to be dy over dx, and that is our slope of the tangent line. That's what we're looking for. And d over dx of e to the ln a times x, but I'm going to write the x over here so that we don't get confused. Okay, our next step is going to be dy dx equals, and now this is just going to be the chain rule. We're just going to apply the chain rule here. Chain rule. And within the chain rule, we're going to have a multiplication, but that's not going to be a big deal. Actually, we're not going to have to use the product rule, though, because ln a is just a constant. It's not a variable. So it's just going to be kind of, we're treating it like a number times x. So we're going to derive it as if it was just an x with a constant in front of it. So that is actually going to be the derivative of e to the x ln a. The outer function, I'm going to write this as f of x is the outer function, is e to the x. And the inner function, g of x, is going to be x ln a. And this is going to be f composed with g of x. Okay, just to make that a little bit clearer, I'm actually going to change colors here. All right, so we're going to have the derivative of the outer function, which is just e to the x, so it's just going to be e to the x ln a again, multiplied by the derivative of the inner function, which is x ln of a prime, right? I'm going to make that a whole nother step. So that's going to be new color. We're going to need a new color to keep things easy to understand. Okay, so now we're going to derive x times ln a, and since that's just a constant, and x has the exponent 1, we're just going to end up with ln a. So we're actually going to end up with ln a times e to the x ln a. And now we're going to remember that e to the x ln a is actually a to the x. I'm going to write it out the long way so that we don't get confused. It's e to the ln of a to the x. And then we're going to remember that this is just a. So our solution is going to be d by dx, dy over dx. dy over dx and d by dx sound very similar, so one can get them confused, but one ought not get them confused. So it's going to be a to the x times ln of a. And again, we're going to write that in front of the ln a so we don't start to think that it's ln a times a to the x, and then things just fall into disarray. Okay, so that's our first way of deriving a to the x. This is what we're going to try to derive another way now on the right. This is going to be probably actually a little bit easier. The second way is a little bit easier. It really depends on your preference though. Okay, so we're going to, let's take some different colors now. Let's take pink. Okay. The first thing that we're going to do here is take the natural log of both sides. So we're still dealing with a to the x equals y, okay? So we're still saying let a to the x equal y. And so now we're going to take the natural log of both sides. And again, we're going to sub in y for a to the x, and then we're going to change it again at the end. It's the same thing. We just have to remember that when we write things differently to solve them more easily, that at the end, we write them the way that we started out writing them again. Okay, so we're going to take the derivative of ln y, which is ln a to the x, right? And we're going to take the derivative. No, that's not right. I'm sorry, I made a mistake. What I'm actually going to do, I'm not going to sub in y for a to the x. That's on the other side. I don't need to sub in y for a to the x because it's a natural log. Aha. Okay. So that just shows the kinds of mistakes we can make with problems like this. What we're actually going to do is remember that log anything, make it k, log k of a to the x equals x times log k of a. That is the rule that we are using here. And that's going to be a very important rule when you differentiate logs. It's going to be a very important rule when you differentiate logs because it means that you never have to deal with powers. Never, ever have to deal with powers when you're differentiating a log. So, okay, so what we're going to do is that. So that means that we can actually just take this x in front of the ln a. So when we're deriving this, I'm going to write it down anyways, though. I'm going to write down, okay. Let's not do that. I'm going to write down d by dx of a to the x. No, that's not right. Of x times ln a equals d by dx of ln y. And that's going to become a product rule right here. That's going to be a product rule. Now on the right here, we're going to remember that the differentiation of any ln x is 1 over x. So let's write that down. Let's write a little note because you want to document your process as you go. Ln x prime is 1 over x. Okay. All right. Now let's change colors or things are going to start to get confusing. So this is going to become x times ln of a prime plus x prime times ln of a equals 1 over y times dy over dx. And the reason for that is that there is a chain rule here. There's a chain rule here. Chain rule. We're going to treat ln x as the outer function, y as the inner function. So we're deriving ln x, putting the inner function into the variable of the derivative, and then we're going to multiply by the derivative of the inner function, which is dy over dx, which is what we're solving for. This is going to be what we're solving for right here, because that is the slope of the tangent line. So now we're going to end up with x, let me write my equal signs, x times 0, because ln a is just a constant, plus 1 times ln of a equals 1 over y times dy over dx. Okay, so the left side is just going to disappear pretty quickly. X times 0 is 0, and 1 times ln a is just ln a. And then we're going to multiply by y, both sides by y, to get dy over dx alone. And we're going to end up with dy over dx, and this is our final solution, equals y times ln a. And that equals a to the x times ln a, because y is a to the x, right, over here, right here. So that is a to the x times ln of a. So we got to the same conclusion both ways. Both ways are fine, whichever one you like best.